All right, today is Wednesday, April 14th. I'm going to go over the review starting on page 7. So, do we remember the two integrated rate laws? For a first order, remember what it is?
The natural log of something.
Concentration of A at any time t is equal to negative KT. I can never remember if it's plus or minus.
L and zero?
I think it's plus then ln of A initial. Okay? So, when we compare the natural log to time, we get a straight line. If it's zero order, just concentration versus time, it's going to be a straight line. And then the second order is 1 over concentration of A at time t is equal, I think this one's positive KT, plus 1 over the concentration of A initial. Now, if those equations aren't right, then I can just look them up here. Well, I'm probably just look them up to make sure. But they're given on your equation sheet, so it's not like you have to memorize them. But I don't want to give you wrong information either. Minus KT plus natural log. Why do I got myself? Okay, so these two are right. So these are just graphs because, again, remember, this is y equals mx plus b. So it's just a fancy form of your linear equation when you have this right here. So we just look at the y-axis. Again, it's not labeled first order, second order on your equation sheet, but this one's listed first, this one's listed second. Okay, so you kind of keep that straight. And then you just have to look at natural log. Okay, so that's going to be this one, that's going to be first order. 1 over is going to be second order. Okay, so you don't really have to memorize all of that. And just remember, slope is equal to, it's always, the K is your slope. Okay, but this is negative, and so you got this is a negative slope. K is always positive. K will be the negative slope, but on the other one, the slope is positive. There's another person.
Or more.
So this one is positive here, so this is just slope equals K. All right. Page 8. Now this one is real important here. This graph, before I give the answer, how did you guys determine, how can we determine what the order of this reaction is when you don't know anything?
The half-life.
The half-life. On the practice problems that we did, they gave you data, rate data, of time versus concentration. If the half-life remains constant, what order is it? First order. So you can always kind of use that as a fail-safe. If you can't figure out how am I supposed to tell whether this is first, second, or zero order, see if there's some way to figure out the half-life. Okay, and if it's the half-life, it's going to be, first order, because 0 and second, the half-life changes. And so I have the equations right there for half-life. So as your concentration changes, so does your half-life here, whereas that's constant. And again, you have concentration value in here, so half-life is going to change on 0 and second order. Now, in years past, I had them exclude this next section, but we'll just look at it quickly. I have never seen graphs like this on the AP test. Does everybody have the half-life stuff copied down? I'm waiting.
So, which one would that be? You just,
Explain how this could be used to determine whether there is first order, second order. You must include all three possibilities in your answer. Okay, well, what you would have to, it's really not detailed enough. This is your time, how does your concentration as you go from 5,000, you know, you would have to know, get a little bit more specific time so you can tell whether or not it's exactly, you know, concentration's going in half with a certain amount of time. This scale just doesn't give you enough accuracy down here, really, in my opinion, to be able to do it. Again, every single one that they gave that we did as a practice problem, it was first order, and we used the half-life, and you can just see that it went. Now, you're gonna have to give an explanation, so that's why you gotta remember to check half-life. Okay, so on these graphs, when is equilibrium reached? How do we know when equilibrium is reached? When they level out, when the concentrations become constant. They don't have to equal one another, the concentrations just become constant. All right? Now, here, we're getting more product. Now, I kind of just thought that this was a hyperbole, but then someone said, no, if you look carefully, you might be able to see that this line is doing that, and that line is doing that. Okay? I didn't see that part, but someone pointed that out and said, so this would be a very product favored reaction. What do we know about the kinetics of this one? Super fast. Because it reaches equilibrium almost immediately. Okay? Whereas, now this says which one is slowest. One of these says which one is slowest. Well, that would be where this one is the farthest to the right. Okay, it reaches equilibrium last. This is the slowest one, in my opinion, as far as when it goes level, the farthest over. I don't know. This one is there. What is it, there? Do what? It's farther to the right. Oh, maybe is that where it's darkened right there? Do they darken it? And then this one is here. So this one would be the slowest. Just that's when it slows down and crosses, goes horizontal, reaches equilibrium at the last point. Is this going to be a reactant or product favored? Reactant favored, because you have very little product being formed at all. Okay, which one's going to, where the K is going to be closest to 1? When the concentrations are the closest to being each other, because products over reactants. All right, I don't want to spend too much time on those. If you know that, you're fine. Page 8. Page 9. Okay? The graph below shows progression of the reaction 2NO2 going to N2O4. Suppose NO2 was injected into the mixture at the dotted line. Sketch what would happen to both concentrations each if NO2 was added until its concentration reached 0.03. Okay? So if I add NO2, what's going to happen initially to its concentration? It's going to go up. So right here, it's going to spike up to 0.03, right? Then what's going to happen to it? It's going to start coming back down. And then what's going to happen to this one? it's gonna start going up, and I don't know if it's gonna spike up or it's just gonna start going up some more until it levels off again and reaches equilibrium. Okay? Now, I'm trying to think of, on this one, if the temperature remains constant. K is gonna equal N2O4 over NO2 squared. What's the only thing that's gonna change that value of K? I'm questioning the only thing that's gonna change K is a change in temperature. Are they talking about a change in temperature at all? No, so the ratio of N2O4 to NO2 at the end has to be the same as it was at the beginning. Okay? Which means that we're going to end up having basically the same concentrations at the end. So this is going to spike up, but then it's going to come back down to here. So as it spikes up, the rate, it seems to me like this one's going to kind of do the same thing. Because it's going to have to start coming back. Again, I've never seen a graph like this on the AP test. So, biggest thing to know, the ratio is not going to change even though you change concentrations. This is going to increase, this one's going to decrease. Oh, that's what it's going to do. Sorry. This one's going to come out here, but this one's going to come down to here. I probably won't even do that. Probably just be more like that. Okay? Because this one's going to increase. When this one's going to go up, and it's going to start coming back down, but it's going to be greater. So that one's going to be less. No, that doesn't make sense either, does it?
Would it not be like the Chalet's principle?
Yeah, it is Le Chatelet's principle. So it's going to speed up going that way, but then this is going to increase, and it's going to start coming back that way until they balance out again.
Would they both like move up?
Yeah, wouldn't
slightly?
they both get, both go up?
And then they would like level out just higher than who they were.
So we're saying like this.
Yeah.
Yeah.
All right, I can live with that. This is the biggest thing, is it's going to spike here, then start coming down, but they both end up having to be, the ratio has to be the same. That's the point I want you to get. The ratio is going to be the same. All right. This one's a little bit, oops, I'm going to put these. This one is super important that you know. Because this graph is all over the AP test. So, I don't want to give all the answers out right away. Represents a solution that has buffering capacity. When is there a buffer created? At what points?
B, C, D.
B, C, and D. Okay? This whole section here is a buffer. Where's the best buffer? Because that's when it has 50-50, it can handle the maximum amount on either side. The only species present is the protonated form of the acid. In other words, just HA. Where's the only place HA is the only thing? A. pH is calculated from the excess NaOH. F. The only species present is the deprotonated form, A minus. E. That's why we have to calculate the pH at this point based upon the salt, not HA. Up until this point, we use HA as the equilibrium, HA going to H plus and A minus. Okay, these concentrations, the H plus, the A minus and HA are changing. But here, we only have the salt. obviously the equivalence point is point E, point at which pH equals pKa.
C.
C, and remember, we've seen that on the test, we've seen multiple ways in which they ask that question. pH equals pKa. And AJ is greater than A minus,
A.
A and B. Okay, AJ is less than A minus, D, E, and F. Okay, obviously D is the point that on the AP test, the questions that we've done, it was always here. It's less here, it's equal, it's greater than here, but its reality is that AJ is just going away the whole time. And best place to determine the molarity of the acid if the acid dissociation constant is unknown. The molarity, the best place to determine the molarity of the acid. If you don't know K. What did you say? YE.
That's where you find the pH.
E is the correct answer. But why?
That's when it's all used up.
Yeah, so how do we find the molarity of the acid? Okay, I heard somebody say something, I'm hearing mumbles. What'd you say?
I don't know.
It's something with the salt.
No, it's easier than that. How do we find the molarity of the acid if we're using the graph?
See how much.
We know 20 milliliters of the NaOH, right? Generally, we know the concentration of this.
MAVA.
MAVA equals MBVB.
Right.
We find that right there at the equivalence point. MAVA equals MBVB. All right, so now, for some reason, there's page 10. Oh, that's the one we're on, so page 11.
I don't know what I thought of it.
I think you skipped one.
I did?
You skipped J, K, and
I
L.
know it was
Page 9, page 10. Some reason or other I didn't have answers to, here's page 10. pH is controlled by the conjugate base. What's the conjugate base of HA? A minus. When is the pH controlled by A minus alone? At the equivalence point E. That's how we find the pH at the equivalence point. We have to, remember we have Ka, so we have to use Kw over Ka to find Kb. Well, in this case, it was a weak acid with a strong base, so we had Ka to find Kb, it's Kw over Ka. Then we have to find the concentration of the salt, which was the dilution problem. That's the most challenging thing. Then once we have that, then we plug it into the expression and find OH minus, find POH and pH. Okay, a buffer where HA is greater than A minus. What point was that? That was B. And a buffer where HA is less than A minus. D. Those are the ones that get asked a lot. That question right there. Okay, so now here's the same thing in reverse. Okay, so we have a weak base and a strong acid. So what type of salt's made? An acidic salt. Notice the pH at the equivalent point is below 7. Where is CH3NH3 plus greater than CH3NH2? Okay, so remember, we're starting with CH3, NH2. We're adding the acid, and we're making it go to CH3, NH3 plus, plus OH minus. Okay, that's the reaction it's going to have with water. Okay, oh, not minus. So it's going to here and here. So when you add acid, you can think of it as two things. Is you're adding acid, is the acid's putting an H plus on there, or it's reacting with this, making more water, and that's forcing the reaction to the right. Okay? The best thing to do is you're adding acid, you're adding H plus to this, going to that. So, when is this going to be greater than that? Okay, D, E, and F, but really, it's probably looking for D. Buffer, where the, well, now I have D and F, we'll go there, but the buffer where this is greater than that. That's D. Best place to determine molarity of the base if the dissociation constant is unknown. E. MAVA equals MBVB. The only species present is the protonated form, the CH3. The only thing that's present is this one. When is that? This one. E. This is point A. This one is the only thing present in point A. This is the only thing present in point E. The equivalence point obviously is E, the point at which POH equals PKB. C. Represents a solution that has a buffering capacity. B, C, and D. And then this, the deprotonated, is greater than the protonated. A. pH is controlled by the conjugate acid. E. pH is calculated from the excess strong acid is F. Buffer where the positive is less than this. B. Y'all, those two graphs are really important to understand all those points. Okay, so when you're studying acids and bases, make sure that all of those are good things to be very much aware of. Okay, does anybody have any questions on this? Explain why pH is acidic at the equivalence point of the Titration or any equilibrium reaction. What's going to be reacting at the equivalence point? The conjugate acid, which is which species? CH3 and H3 plus in water. What's it going to make?
CH3 and H2 plus H3O.
It's generating H3O plus. So again, in terms of our three definitions, why is this an areneous acid? Because it's producing H3O plus. Why is it a Bronsted-Lowry acid? Critical what? It's donating the proton, donating the H to the water. And then in terms of Lewis, water has the two lone pair on it, so the lone pair are being donated to the H plus. So this is an electron pair acceptor because the source of the H is this thing. Okay? But this is going to be the equilibrium. It's always going to be the salt going the other way, going back to the base. And again, since it's a weak base, this is a strong acid because it really wants to get back into this form. So the conjugate of the weak base is acidic, and it produces the H3O plus ion in water. All right. Page 11. The titration curve of diprotic acid, H2Y, with a strong base is shown. Now notice, with a diprotic, there are two equivalence points, because each hydrogen comes off one at a time. Okay? Write the equilibrium reactions for that, and the acid dissociation constant for the sequential removal of the proton. So it's simply going to be H2Y going to what? HY minus plus H plus. And then HY minus is going to go to Y2 minus plus H plus. Now the only thing I can think is they want the expression. You can't calculate K from this because you don't have any information. Okay? But you can say that K1 is equal to H plus times HY minus all over H2Y. And then K2 is going to equal H plus times Y2 minus all over HY minus. Now, what do we remember? What's the Y2 minus going to equal? Y2 minus concentration. As
HY or H plus.
no. It's going to be the same as. What do we know about these concentrations right here? Once it goes in, this goes here. What are these concentrations? The same. So when you put those into here, your H plus and your HY, they're going to cancel out. Now it's going to be plus X and minus X, but X is going to be negligible. So the Y2 minus is always going to equal K2. Remember the H plus, the pH is always just going to be based upon the first one, because the second one's going to be minimal. For the acid H2Y, write the formula of the species present next to each number. Okay? So what's present here? H2Y. What's present here? Just HY minus, and then here, just Y2 minus. All right, so number 6. This was actually on an AP test in 2013. When I first looked at it, I said, man, that's complicated, but then when I stopped, notice that this is a solid, aqueous, aqueous, okay? Conductivity can sometimes be used in place of pH to monitor a reaction. Which graphs below represent the change in conductivity for the following reaction as it titrated past the equivalence point, okay? So past the equivalence point. So you have, you're adding H2SO4 to a solution of calcium hydroxide. So as I'm adding H2SO4, what's happening to the number of ions in solution? And they say write the net ionic equation. I know here, there really is not going to be a net. There's no spectators here. Because solids and liquid, both on the right-hand side, only aqueous break apart. So what's going to happen to the number of ions in solution as we begin reacting? For every one of these that I put in, it's going to react with that, right? So adding H2SO4 is not going to be increasing the ion concentration. Because every one you add reacts with this and makes a solid. So what's happening to the ion concentration as it's reacting? It's going down. Until all of this is reacting with all of this, and there's none of this, and there's only that. So we get to near zero conductivity. But now why does the conductivity go back up?
There's more ions circulating.
Because now you're adding past the equivalence point, now you're adding more H to S of 4, so the number of ions begins to increase again. That's a good one. Now I know that because of over here, I'm not making any ions over here. If I had spectator ions to where I had some aqueous forming over here, well then the conductivity would remain the same. Because you're keeping pretty much the same amount of ions. Last page. Beer's Law, random lab. Beer's Law is a favorite to ask questions about, lab questions. So just remember that absorbance is equal to ADC, your constant times your path length times your concentration. These two things are generally constant. So it's Y equals mx plus b. Well, actually it's y equals mx right there. B is 0 because of 0 concentration and 0 absorbance. You are not going to have to calculate the molar extinction coefficient as that. So don't even worry about that. Now, this was a question I asked. Why was NaCl not something we can use in a Beer's Law lab? Because it's colorless. You have to have some color in the solution for the spectrophotometer to pick it up. Okay? Where are your colored metals? Your transition metals. But again, remember zinc and cadmium, because that D sublevel's filled, the electron cannot transition between the 4s and the 3d, and so they end up being colorless. All right, the cuvette was not rinsed with solution prior to filling with the cobalt-2 ion solution. Okay, remember you always want to rinse it with the solution because the water would dilute, lowering the absorbance. I really don't know the answer to B. I tried to look up the answer to B. I don't know what it is. You're not getting as accurate results because you want maximum absorbance. As remember on the graph, you want it to where it's going to absorb the most. It's where you set the wavelength, but I'm not sure how to change the wavelength. You just get less accurate result, but I don't know if it's above or below. I would say you get less absorbance one way or the other, and so it's going to affect it that way. If you had a fingerprint, is that going to cause it to absorb more or less? More. And then filling above the line has no effect. And then these graphs here just are way more confusing than they're worth. Nope, I'll leave that on there if anybody needs that. All right. But wait, there's always more. Does anybody have any questions at all about anything on this, pictures and diagrams? I thought it's a pretty good overall review. There's some stuff on there that's a little bit more picky than what it needs to be. But overall, some good stuff on there, especially the acids and bases stuff, the kinetic stuff.